All right. Hello, everybody. Dear everybody. I am David Bromberg, professor at the University of Rennes, and I'm going to sharing the session and to sharing the committee for the habilitation à diriger les recherches of Johann Bourcier. And I'm going first to introduce the committee and the different members. I'm going to start by the reviewers. So traditionally we are introducing the first reviewer. So we have Gordon Blair from the University of Lancaster, professor at the University of Lancaster. And then between Grenoble and Lyon, I don't know really. Grenoble is the farthest. So then we have Lilian Kema from Grenoble INP, and then we have Sonia Ben Mokhtar from CNRS. From CNRS, so the affiliation is not really correct. And
I don't know why.
We have the different external reviewers, examinators, more exactly. Laurent Réveillère from the University of Bordeaux, and Gaël Thomas from the Telecom INP. Sud Paris. Telecom Sud Paris. Okay. This affiliation is correct. And also Jean-Marc Gézéquet, professor at the University of Rennes 1, and myself. So you have 45 minutes, and you can start as you want.
Thank you, David. Welcome to my defense of my habilitation à diriger les recherches. I've entitled this work Software Engineering for Self-Adaptive and Open Systems. So I wanted to start by a motto, which is software is eating the world. This motto was coined in 2011 by Mark Andreessen, and it's actually illustrating the fact that nowadays we are surrounded by software and electronic devices, and it's everywhere. We interact with software all the time without even noticing it. And what I want to emphasize here is it is not just that we are surrounded by electronic devices, but these electronic devices have complex, adaptive, configurable behavior, and this behavior is realized through software. So, to illustrate this fact, I follow Bob in his daily routines, and the particularity of this slide is that all devices presented on this slide are commercially available today, so it's not science fiction, but it's really now. So Bob is waking up in the morning through a smart connected alarm that simulates a sunrise. Then he has a smartwatch that tracks his activity during the day. He orders his coffee from his smartphone because he has a connected coffee machine. When he is going to the bathroom, he uses smart connected scales in order to weigh himself. Then he goes to work with an electric connected car. And when he's coming back home, he goes to the gym. He has a connected bicycle to tailor his activity to what he is. And when he's coming back home, he has smart connected refrigerators that can suggest recipes based on the ingredients. And he also has a smart thermostat that is adapting the room temperature according to his habits and so on. So this is really now. And this is an execution environment where we can deploy software, and the software, this execution environment has the following properties. The first property is that it's distributed, so there is many devices communicating together. It's heterogeneous, so all devices have different capabilities, and it's dynamic, open, and unpredictable, since devices may appear, disappear, enter, go out of the networks, and it's unpredictable because this can happen whenever something happens. So So this is true and this is visible in our daily life, but this is true for many application domains. So for example, when you came here, you might have seen the smart autonomous bus running around the campus. So basically this bus, the driving part is realized through software. So we have software everywhere. We have software in e-health and elderly support at home. We have software in energy and smart grid systems with all the renewable energy production systems. We have software in environmental monitoring, intelligent transportation systems, cloud infrastructure, precise agriculture, and so on. So it's everywhere, and since software is everywhere, we as humans and users of the systems, we rely more and more on this computing technology to support us in our daily life. So if we rely more and more on this technology, then we are expecting these systems to deliver good services to us regardless of the situation. So no matter what happens, we expect these systems to work and to deliver good services to us. So this poses us some new grand challenges as software developers. So software developers have to cope with these new environments and with this new expectation from the users. So there are many grand challenges. I'm listing a few here and I'm concentrating on the two last ones. So energy consumption of the system is something we have to deal with when we produce software. Software interoperability, because we have to make these different systems to talk together. Software coordinations to coordinate the behavior of each thing. Software testing is important for this kind of environment, and it's a complex challenges, and so on. So the two grand challenges I'm going to focus on in this presentation is software automatic deployment and configuration, and self-adaptive software and fault tolerance. So to situate my work in the research landscape, we have, I consider myself as working at the frontier of three domains: software architecture, self-adaptive systems, and model-driven engineering. So from the software architecture part, I'm inspired by the work made in component-based software engineering, service-oriented architecture, and more recently on the microservice architecture approach that has been proposed. Between the software architecture and self-adaptive systems, there is this seminal work of K-loop that is a generic architecture for realizing self-adaptive systems. On the automatic decision parts of self-adaptive systems, we have ECA rules, constraint programming, search-based optimization, and software engineering. So I'm inspired by all these works, and I'm also obviously inspired by all the work in the modeling community with modeling framework, and more recently, the paradigm of model at runtime. So I will now move to the contributions of my works. I've entitled my contribution "A Generic Architecture for Designing Self-Adaptive Systems in Open, Distributed, and Heterogeneous Environment." So here I present my contribution. This architecture is visible here. So we have the distributed system in gray here at the bottom of the figures with all devices and the cloud and everything. And then we have in the middle this runtime modeling layer that is actually a model at runtime, and this is the cornerstone of the approach. So it is supported on one side by a middleware that is in charge of synchronizing the systems with a runtime modeling layer, and that is also in charge of monitoring and reconfiguring the systems according to this. Then we have this runtime modeling layer that represents the states of the distributed systems. And then we have, on top of this modeling layer, we have a decision-making layer that, according to the states of the systems, decides what to do upon the systems. So this is really the global approach that I followed during all the work I've been doing until now. And I'm going to present the various contribution on this particular figure. So I've been working with several PhD students, and I'm going to situate their work in this figure. So the first one is Francisco Acosta. He has been investigating the question, is it possible to provide a middleware supporting model at runtime paradigm on top of very, very small nodes? So I'm talking here about nodes with 64 kilobytes of RAM and Cortex M3 CPU. So basically these nodes are supposed to run on battery for some years. And we published this work, and we had some interesting results. I've also worked with Inti Gonzalez. He was doing a PhD in the team, and Inti works on resource management and monitoring on shared execution environment. So we had a contribution on resource monitoring and reservation. We published it through conferences, through tutorials, and we also published it in journal papers. On the decision-making part, I've been working with Ivan Paez. So Ivan Paez was working on the question, is it possible to adapt the systems before a problem happened? So it was, the idea was to do proactive adaptations, and we had some results in self-adaptive sensor networks. We were leveraging time series analysis in order to predict the future of some specific values and adapt the system beforehand. Then I've been working with Jackie Bourgeois. So Jackie Bourgeois was pursuing a PhD in co-tutel with the Open University in the UK. And Jackie was working on applying the whole approach on a specific problem. The specific problem was optimizing local energy consumptions when using solar panel. And the focus of his PhD was on user acceptance and HCI. And basically, he did an experiment with 18 households in the UK running for 6 months. I'm currently working with Ludovic Moulin, a PhD. So he should defend his PhD in 1 year if everything goes well. He is working on the runtime modeling layer. So we've been working on adding time dimensions to this runtime modeling layer. So we had some contributions, and this adding this time dimension basically helps the decision-making layer, because you store both the history and the planned futures, and you can reason about the systems knowing all these time dimensions. So we had some contributions. We also had contributions on diagnosing these self-adaptive systems, because as long as you store the history of what happens and the decisions that were done, then you can diagnose if something has been wrong in your self-adaptive systems. And we are currently working on adding uncertainty management in models and language, because when you gather data through sensors, then there is a certain uncertainty associated with the data you're basically grabbing from the reality. And then we want to keep this uncertainty up to the decision-making layer in order to take it into account when we take decision. So I've also wanted to highlight two main past collaborations I had. So the first one is Dionysos F. Statue. So Dionysos Efstathiou was pursuing a PhD at King's College London, and we were working together in the framework of a European project, and we had a quite strong collaboration, so I wanted to put this forward. So we were working on the decision-making part, and we were working on making evolutionary algorithm faster to make them able to cope with runtime decision-making. So we had several contributions together. The main one is the surrogate-assisted optimization of composition application in mobile ad hoc networks. And I also wanted to emphasize the collaboration with François Fouquet. François was doing his PhD in the team, and then he left to Luxembourg, and we maintained a strong collaboration when he was in Luxembourg. And we worked on the runtime modeling layer. So we've been working on making the model at runtime able to cope with distributed and dynamic systems. And we had several contributions in conferences, in tutorials, and we also had another contributions on the decision-making part, where we were looking at how we can optimize multi-objective evolutionary algorithms to cope with time-aware decisions we have to do. I also wanted to emphasize the last contributions that were not done with students, but it was done with, within the framework of a European project, and it was done with more senior people. Some of them, you know them, Benoît Baudry, Olivier Barret, Franck Fleuret. And basically we were working on the idea of diversifying the systems at the beginning in order to make it more resilient. So basically we were adapting the system even before anything happened to make it more resilient, more fault tolerant. So this work was published in IEEE software. Now I want to emphasize projects collaboration. So all this work is done in collaboration with many people, but also in many different projects. So I've been working on European projects, so the Relate ITN project, it was more on the decision-making part. The FP7 FET Diversify project, which were the more between runtime and decision-making. The H2020 ads, which were really on the runtime modeling layer and the middle layer. And currently we are working on the H2020 stamp that is really on the testing part of these systems. I've also been working on more national projects. So there was this infra JVM project, which were really on the Java virtual machine. And we are currently working on a regional project that is a laboratory of excellence project. It's called Profile, and we work on privacy data. I also had direct collaboration with industries through a CIFRE collaboration with a company named Faber Nobel in Paris. And through two common labs from Inria, so one with Nokia Bell Labs and one with Safran. And I also had two collaborations, direct collaboration with other academics outside of France. So it was the two co-tutors mentioned before, Jackie Bourgeois and Ludovic Moulin. So during these projects and on other aspects, I had collaboration with many people in and many institutes. So I want to emphasize this on this slide. I've been working with SANTEF in Oslo, SNT in Luxembourg, Trinity College in Dublin. Karlsruhe Institute of Technology in Germany, King's College in London, Charles University in Prague, KTH because Benoît Baudry moved to KTH in Stockholm, Imperial College in London, SEERC is a Southeast European Research Center in Greece, UPMC in Paris, University of Bordeaux, and University of Rennes too on social aspects of this work. So I also wanted to mention on this slide the competitors we have in this work. So the competitors, basically we have collaboration with all these guys, but we also compete with all these guys. So there are the natural competitors, maybe except University of Rennes too, and we do have other competitors. David Garland on the self-adaptive and software architecture part, Sam Malek on the same part. We also have identified Nelly Bencomo on the model at runtime part, and obviously also probably all the members of the jury, because if you're here it's because you know what I'm talking about. So obviously I cannot go into the details of every contribution, so I've decided to dig a bit deeper on one specific contribution, that is Scapegoat, which is resource monitoring in shared and open execution environments. And why I've chosen this work is because firstly I'm really proud of this work. So I really like this work and I'm really proud of the way we conducted the work. The second reason is that we apply self-adaptive mechanisms to the monitoring part. So we will see this later, but it's kind of a recursive thing. So we apply self-adaptive on the monitoring part, which is part of the self-adaptive loops. So this is kind of interesting. The third reason is that it's a work that inspires my future research projects, and I will explain why at the end, when I will explain my future research project, but this is one of the works that heavily inspires the future research. And the last reason is that we have done this work through a specific scientific methodology, and I'm really proud of this scientific methodology, and this is the one I want to emphasize for the works I'm doing, and this is the one I want to try to make for each contribution. So Scapegoat is a work that were done together with Inti Gonzalez and Olivier Barret, who was supervising the PhD of Inti with me. And basically it focuses on resource monitoring in shared and open execution environment. So really the focus is on the arrow of monitoring, so going back from the system state up to the runtime modeling layer. And the grand challenge here is how do we perform this resource monitoring while keeping good performance on the systems. So this is really the challenge. So to dig a bit deeper in the specific context of Scapegoat, we are targeting open, dynamic, and shared execution environment. So this kind of environment, and this work was done within the framework of the Infra JVM project. So obviously it works on Java-based machine, and we assume that the software is realized through distributed software components. So here we have a very sketchy example of an application which is composed of 4 software components, and these components communicate together and they are deployed on different Java virtual machines. And the open and dynamic aspect is that basically we can deploy a new applications on top of this infrastructure that only shares the environment. And the thing to notice is that if this, for example, this green boxes, this green software component starts to consume too much CPU, then it will impact the other application that has absolutely nothing to do with this one. So this is something important. So the objective of Scapegoat is to do resource monitoring in shared, so we can deploy several applications on the same environment, and open environment. And the goal is to spot suspicious behavior regarding resource consumption in this environment. So the state of the art is that monitoring mechanisms exist. We know, everybody knows them. But they introduce a very high overhead on the systems. And the thing is that if you introduce too much overhead on the systems, then you cannot use this monitoring in production, this monitoring system in production. So the goal is really to limit this overhead. So the idea we have is to use an optimistic approach for adaptive monitoring systems. So the optimistic part means that as long as everything goes well, then we don't need to monitor in details. We want to monitor only if something wrong happens. So the idea is to add resource consumption contracts on top of each component. So we add the contracts on top of each component, and then we only monitor global consumptions. As long as the global consumption of the system is good, then we don't do anything any more thing. The global monitoring consumption has a low overhead on the system, so we try to be in this state as often as we can. And then, if something happens, we introduce precise and localized monitoring when we detect problem, but this has a higher overhead. So the global picture is that we have resource consumption contracts on top of each software components, and then we enter the global monitoring states. And if possible, we stay in this state forever. But if something wrong happened, we have an alarm that is raised, and we go to the suspect selection. So the suspect selection is an activity that is in charge of guessing which component is probably faulty. So we use heuristics to do this. I will explain the heuristics in the next slides. And we select the component that is probably faulty, and we introduce some probes. So we inject probes dynamically in order to monitor very precisely its consumptions regarding resources. If we find out that the software is guilty, then we reconfigure the systems and we go back to global monitoring. If we find out that we were wrong, so the suspect is not behaving abnormally according to resource contract, then we go back, we stop the precise monitoring and we go back and we follow an iterative process here. So the type of contracts we have here is a contract that specify maximum resource consumption usage over a specific period and optionally under certain operation conditions. So we have, for example, peak number of instructions per second, which targets the CPU. We have maximum memory usage in general, so which it targets the memory. We could have a peak bandwidth usage for I/O, and we can also specify the operation conditions. So as long as we stay below 100 requests per second, then the memory will stay below 30 megabytes. If we have more than 100 requests per second, then we cannot ensure that we stay below 30 megabytes. On the probes, the specific probes that we inject dynamically, so the first thing is that we can dynamically activate and deactivate these probes. So that's really important features. And the second thing is that these probes are automatically synthesized based on the contract. So if the contract doesn't talk about memories, then we will not synthesize the memory instrumentation part. We will only synthesize the part that we really want to monitor. So we have two memory instrumentations probes. one which is a bytecode instrumentation, and the second one the leverage memory heap exploration. So the bytecode instrumentations has the drawback that you cannot stop it. So as long as you stop it, then you do not count anymore the allocated objects, and then you cannot follow what's going on. While the memory heap exploration can do a full count, you can deactivate it, but it has to stop to pause the application for a very few times. Then we have instruction instrumentation. Here we use bytecode instrumentations to count basic blocks of code. And we have I/O instrumentation. This is realized through instrumenting selected methods in the GDK to intercept network traffics and I/O traffics. For the heuristic parts, we have simple heuristics and more complex ones. So the heuristic is in charge of guessing which component is guilty. So we have two very simple heuristics. The first one is maintaining the number of previous failures. So if you have a high number of previous failures, then you have a higher probability of being again guilty. And the component with the smallest code coverage. So this is linked with the test. If you have less tests, then you might have a greater probability to be faulty. And we have a more complex heuristics. This one follows the basically it leverages the model at runtime aspects. So the intuition here is that if you can spot a problem now, then it's probably in the last updates, in the last reconfigurations that were made, that you will find the guilty component. So this one, look at the history of updates and reconfigurations, and go and favor these ones to be the selected guilty component. We had we conducted some evaluation of scapegoats. So the first, the evaluation was conducted using a well-known benchmark, the DACAPO benchmark, and two realistic software scenarios. So we implemented two scenarios, one which is a mobile case study, which was done in a use case of firefighters, and the second one is a web server case study, more classic one, but distributed systems. The result is that we were able to decrease up to 93% the overhead in comparisons with state-of-the-art full monitoring, but we introduced a delay to spot the faulty components. And this delay is highly dependent on the heuristics, and here our best result was using history of faults, but this is highly biased by the fault injection model. So this is something that needs more investigation here. If we look a bit closer on the overhead of the specific probes that we dynamically inject, basically on this global picture, what you have to remember is that the global monitoring doesn't really introduce any overhead if we look at the time for executing the application, and that memory and instruction introduce a quite high overhead. And that's what the takeaway from this slide. And then we compare the two techniques for memory exploration, so heap exploration and memory instrumentations. So what we can see on this slide is, depending on the use case, it has different results, but in general, heap exploration is a bit cheaper, and it has good properties that it can be stopped whenever needed. So we advocate the use of heap exploration in this use case. Finally, on this use case, I wanted to highlight the scientific methodology that we follow to evaluate and to actually conduct the work. So the first thing is that we had an intuition that using an optimistic adaptive monitoring system will give better results. So that's the first thing. Then we developed a real piece of software to demonstrate this intuition. Then we defined the research questions that we were really targeting. We evaluate the research questions on a standard benchmark. So if it exists, then we can do it. So this was really an important thing. And then what we did is to develop realistic use cases and again evaluate the research questions on the realistic use cases. And this sometimes gives different results than the standard benchmark. So we really wanted to go to the realistic use cases. So I'm going to move to the conclusion and perspective now. So I'm very, very briefly summarizing the contribution. So the contribution is a generic architecture for designing self-adaptive systems in open, distributed, and heterogeneous environments that is visible on the figure behind these boxes. So what we could take away from all these works. So I've taken out 3 main lessons learned from this work. The first one is that detecting faulty or abnormal behavior in an open, distributed, and heterogeneous system is really a challenge. It's not really easy to detect when something goes wrong, because if you look at the micro level or at a macro level, you have very different behavior. And if you look at the macro level, even if there is many problems at the micro level, then you can have a very good services for the users. And I think that resource consumption statistics profile, such as the one emphasized in Skateboard, is a first step in this direction. The second thing is that, a bit like in the testing community, people are saying that software should be developed with testability in mind. I think that systems should be designed with adaptability in mind. So this will force people to make explicit every configurations, every deployment configuration, and so on. And this will ease decision making, but as long as we start to do this, we also introduce some simple self-adaptive mechanism inside the systems, and this makes the management of larger systems more complex. And I will explain what I mean here in the research project. And the last takeaway is that the configurations space and the situations in which the systems can be embedded is too large to be managed by a developer by hand. So for me, the automatic and continuous improvement of the system configuration is the key to go in these directions, because if you only rely on software ability to forecast all the futures, then it will fail. So the research project I want to propose today, I've entitled it Chaos Engineering as a means to improve software adaptability and dependability. So the assumption is that systems are becoming very complex. They are large, distributed, open, dynamic. They often embed adaptation and fault tolerance behavior. They embed self-defense mechanisms and so on. So here we have a fact that the systems are becoming more and more complex, and it's more and more hard to understand what's going on. So for example, if you take a system point of view, so if you take a macro point of view, it's very hard to assert if a system has a nominal behavior. If I take the example of Netflix, for example, so what they do to know if their system is really working, they are looking only at 2 metrics. The first one is the number of streams that starts per second. So for their whole systems, they look at this number of streams, and they look at the number of connections per second. They look at these 2 metrics, and they know They have a statistic profile of what is supposed to happen. And if it deviates too much from the statistic profiles, they know that something is wrong in their systems. They don't really know the source, but they know that something is wrong in the systems. So it works for Netflix because they have identified these two key metrics, but in general, it's really hard to assert if a system has a nominal behavior. So this is one problem, and the second problem is that when you know that there is a problem, it's complex to find a solution to this abnormal behavior. So my visions for this is to adopt a system point of view, so a macro level view on the systems, and also follow what is called a DevOps life cycle, so an infinite loops of continuous improvement. So my proposition is to go, so this is the loop from DevOps. Here you have the design, here you have the runtime phase. So the first part in the design is to design with adaptability in mind. Then to define what is the nominal behavior and the steady system state. So what is the target that you want to achieve. Then before deploying, check resilience to specific perturbation. So it's really important. And then deploying the system in the execution environment and putting the system in a chaos environment. So I'm emphasizing here chaos as nominal execution environments. So basically the idea of chaos is to increase the rates of failures in order to be sure that the system is really able to cope with failures when they happen. So if you immerse a system in a chaos environment, then you somehow increase its resilience to failure. Then we want to observe runtime behavior and state with a defined nominal behavior. And then we want to discover solutions, and when not possible, we hand over to users, which can be either software developer, decision maker, scientist, whoever they are. So the grand challenges here, I named two grand challenges. The first one I called it runtime system Oracle engineering. So Oracle is really to know if the system is working. So it's someone who tell you if the system is working. And what I'm emphasizing here is that it's a real problem as long as you look at a system point of view. So how do we define these Oracle models? What are the nature of these models? Because we're in the software engineering community, we're used to engineering models, so models to build things. Here it's a different kind of model. It's a more scientific models. It's observing that the system is behaving according to a model. So it's a different kind of models. And then what are the parameters of these models? And how do we validate that these models actually inform us on the real, if the behavior of the system is correct or not. The second grand challenge is chaos as nominal execution environment. So the question here are what type of perturbation to introduce, malicious, faulty, at the hardware level, at the software level, at the resource, at the network level. So this is a big question. And then the second question is at which frequency and at what scales do we want to introduce these perturbations? Because if we introduce this perturbation at a too high frequency, then the system is not able to cope with the messy environment. And if it's a too low frequency, then we don't really know if it's able to cope with real failures. So it's a real question. So I have 3 PhDs that just started this year, and I'm explaining how they go in realizing these visions. So the first one is Antoine Sheeran. He's doing a PhD with Faber Nobel in Cifre. and he is working on the design with adaptability in mind. So his idea is to push back some of the middleware and runtime modeling layer features into the system itself. So we want to add self-describing mechanism in web services to enable some features, composition, test, documentation, automatic parts of these features. The second PhD that started this year is June Benvegnu. So she is doing a PhD with the geology department at the University of Rennes and us. And basically the goal is decision support for environmental science, but the idea here is to study how other sciences represent and validate the scientific model to explain the complex systems. So this is really something we want to do. We do have complex systems now. We have built this complex system. So how do they do this in other science? Because they're used to do this. How do they represent and validate these models? So this is a question we have. And the last PhD is Alif Pranata that started this year. So we're doing this in the context of the joint lab with Nokia Bell Lab. And the title of the PhD is Chaos Engineering for Software-Defined Networks. So we're targeting the software-defined network layers. And the idea is to adapt the chaos engineering principle to provide a kind of test at runtime framework for software-defined networks. And the first contribution we envision in this world is to characterize network perturbations, characterize observable metrics in these software-defined networks, and perform a first sensitivity analysis to determine if a specific network architecture is resilient to some types of perturbation. So this ends my talk, and I'm welcoming questions from the jury.
Thank you very much, Johann, for your presentation.